Hello everybody, and welcome to the Cybersecurity on R&M panel session. I appreciate all you guys for coming today. My name is Bryan O'Halloran. Unfortunately, I'm unable to be there with you guys today. I am supposed to be the moderator of this panel session, and due to some travel issues, I'm unable to make it. That said, a little bit about me. I am an assistant professor at the Naval Postgraduate School. Previous experience is at Raytheon Missile Systems. My research interests are in things like risk, reliability, and safety, engineering and design of complex systems, things like design theory and design methodology, as well as these early types of design efforts like functional design and conceptual design. And then I've provided my contact information here in case you guys are interested in getting a hold of me after the session. So the question is, why are you here today? What topic are we going to be discussing? Today is actually not as much about talking to results like we typically see in these RAMs or other conference sessions. Today, what I'm hoping for is a little bit more of a discussion-based session where we can present an idea and we can talk about it and come up with some thoughts on it. And specifically, the topic that I want to bring up today is this idea of cybersecurity on R&M, and specifically as it relates to physical systems. So some of the topics and terms and semantics that I think play into this topic include cybersecurity, security, physical security, and specifically to physical systems, again, or complex systems or cyber-physical systems. Some other terms that are kind of affecting this area are cyber assurance, system control, Internet of Things, smart cars, smart homes, smart cities, such as, for example, Singapore as a smart city, wearable technology, and network theory. And that's just to name a few. There are a lot of other areas that are going to impact the topic I'm going to bring up today. So the first thing I want to talk about is connectedness. And if you think about devices and the internet, we know that consumer electronics are growing at a rapid pace. We know that the internet is, of course, growing at a very rapid pace. In fact, in 2003, there were 500 million devices connected to the internet, which sounds like a lot, but in 2016, there were 12 billion devices connected and 3.4 billion internet users. So the idea here is that what used to be non-existent is now a massive network of connections, and as every device is connected to that network and part of that network, they share connections through that network. The graph on the left side, the bottom left of the world, is showing the top 0.1% of attacks that came through the internet just on January 20th. So this is one day. Each line represents one attack. This is showing you the top 0.1%. And although there's not a ton here, this is just a very, very small amount of attacks that are occurring. So the idea is that we have a society that's becoming highly connected through devices, and we're also in a situation where the number of attacks are going up significantly. I've got some example attacks on the bottom here, such as the wormhole or sewage pool, the sinkhole, hello world. These are just a couple of examples of many different types of attacks that exist. So what type of things are connected to the internet? As an example, there are things like smoke detectors, animal health monitors. For example, the cow here in the middle has a monitor inside him that measures his health over time so that farmers can be taking better care of their livestock. There are volumetric water sensors such as the Belkin Echo, which measures vibration to understand when the water is being pumped through the system, so it can measure all of that. There are also things like thermostats and production equipment, which is interesting because, for example, if you take the case of the thermostat, this is part of a smart home technology where a user has a device, such as a cell phone or a tablet or computer. They can go into their house and they can actually change the temperature of their house. In fact, I have a friend who has a rental home in Florida. He lives in California. And he says that a lot of times after his renters leave, because it's a vacation rental, he'll go in and he'll adjust the temperature to something that's reasonable, so he's not paying ridiculous amounts for cooling the place when nobody's there. So it's a great technology, but unfortunately every time something new is connected to the internet, it offers a vulnerability to be exploited. If you think about test equipment for complex systems as they go through the production process, a lot of test equipment is connected to the internet, right? And some systems are also directly connected to the internet. So those are offering vulnerabilities. So the question I have to you is, how secure are your systems? Where are those vulnerabilities? Have you thought through that? So I mentioned attacks a couple slides back, so I'll give you a couple of examples of some recent things that have been going on in our world, and this is just a couple of simple examples. Maybe you've heard of some of these, maybe you haven't, but there are many, many examples out there. So this is just a few. First off, at BMW, there were some researchers that looked into one of the more modern style BMW vehicles and were able to break into the car remotely and do things like lock and unlock the car. They were also able to connect to the main systems within BMW and actually control the safety critical functions within the BMW, which means that they could actually deactivate safety critical functions, which of course the user is relying on as they're driving the car. There's the Stuxnet example, where the US and Israeli government agencies deployed Stuxnet into Iranian nuclear enrichment facilities to inhibit their ability to make nuclear weapons. There were activists recently that inhibited the flow of oil from Canada to the US, basically by breaking into some areas and just turning valves. But they were able to obtain some critical information about how the system works in order to do that. So not only did they actually inhibit the flow of oil, so they affected that physical infrastructure, they also gained knowledge. So they kind of exploited multiple attacks. On the far left side, this model that I'm showing is an example that was presented at DEF CON 23, which is a model to train practitioners on how to hack into chemical plants and exploit them. So this is an interesting philosophy because it's training you on how to do things that should not be done, but it's with the goal of showing what some of those vulnerabilities are and a way to educate practitioners so that they can turn around and actually avoid that in their own systems. So it's quite a neat thing going on. Now you're probably wondering, how does all of this relate to R&M? Well, let me run you through a version of reliability history to try to answer that question. So first off, back in the mid-1900s, reliability was born into the idea that we need to fix components. So we had things like FMEAs and FMECAs developed, which traditionally are very much a component-focused methodology for fixing failures. The idea is that over time, as systems became more and more complex and more connected, there were more interactions, we've seen more interaction-based failures. And in fact, suppliers, especially electronic suppliers, have shown that they can produce very, very reliable components. So reliability has jumped through the roof from a component-based stand. But unfortunately, because of the complexity of systems, now we're dealing with these interaction failures. So we can take very reliable components, integrate them in a very unreliable way, and the result is a very unreliable system. But as we start to understand the interaction failures that we're dealing with currently, we're now running into this idea of exploits, where systems are now being broken into and actually exploited by attackers. And this is a whole new level of reliability. So it certainly fits into the idea of reliability because with this, with an exploit to the system, it's possible that the system or part of the system won't function. So it's very obviously part of reliability. But it's something that unfortunately we don't have the methods in place to understand. So what I want to leave with today is the question of how do we start to address this problem? What are ways that we can think about this problem either in design or in production or in fielded units? What do things like stealth and persistence and attack type mean when we go through the design process and we're developing new systems? What about identifying and detecting vulnerabilities in our system, quantifying risk, and so on and so forth? These are important topics that I believe that we need to begin to think about and begin to flow into our design process or understand during production or understand in our currently vulnerable fielded units. Thank you everybody for your time.